Today we're going to look at truth tables, and the first one we're going to look at is the negation. So if P is the proposition that I'm wrong, then not P means I am not wrong. And if I'm not wrong, that means I am right. To set up a truth table for anything, look at all the possible combinations you can have. Now, if there's only one proposition, it's fairly easy because it can either be true or it could be false. Therefore, the negation is if P is true, the negation or not P is false. And if P is false, then not P is true. So in other words, if it's false that I'm wrong, then it's true that I'm right. If we compare this to sets, if we define the set P, which is odd numbers less than 10, then if we were to draw this up as a set, there's P. So we got 1, 3, 5, 7, 9. Then not P is going to be 2, 4, 6, 8. And the area defined by not P is going to be everything outside the circle. Now let's look at conjunctions. Now, to remember what conjunctions mean, look at the fact that this has an N in, and also has an N. So a conjunction is when P and Q are true, or any two propositions. The symbol is the upside down V. Very similar to the set symbol, which is an upside down U. So an example of a conjunction is if P is the proposition that it is hot, and Q is the proposition that it is sunny, if Connie only buys an ice cream when it is hot and sunny, then this is a conjunction. Looking at the truth table for this, there's P, there's Q, and there's our conjunction, P and Q. Now we've got to look at all the possible combinations of P and Q. So you could have P is true, Q is true, but you can also have, when P is Q, that Q is false. Similarly, if P is false, Q can be true, and Q can also be false. Now the and means that the conjunction is only true if P is true and Q is true, like the first line. In the second line, because Q is false, the conjunction is false. In the third line, P is false, so the conjunction is false. And in the fourth line, they're both false, so the conjunction is still false. Doesn't matter that they're the same, because they're false, the conjunction is false. If we look at it in terms of sets, if we define P where X is a multiple of 3, and X is less than 20, and Q is defined as a multiple of 4, also less than 20. If we were to draw this up as a set, there's our P, there's our Q. if we look at, first of all, the multiples of 3, the first one's 3, that is not a multiple of 4. So that goes in there. 6, again, not a multiple of 4. 9. However, 12 is also a multiple of 4, because it's a multiple of both, it goes in there. 15, only 3. And 18, only 3. Now let's look at our multiples of 4. We've got 4. We've got 8. 12 is already covered, because it's also a multiple of 3. And we got 16. So here's our set, and the area defined by P and Q is this area here. So in logic terms, remember it's the spiky upside down V, that is P and Q. Now let's look at disjunctions. Now disjunctions means or. So one or the other proposition has to be true. So if we look at the proposition that Dizzy the disjunction, goes to the hairdresser and gets a cut. And Q, Dizzy goes to the hairdresser and gets a colour. Now, Dizzy can't decide. He might get a cut, or a colour, or he might get both. So that's where the or function comes in. It's P or Q or both. So again, drawing up our truth tables here, there's P, there's Q, and there's our disjunction, which is the V. So that's the symbol for disjunction. So again, P could be true, looking at all the combinations, and Q's true. Or if P is true, Q could be false. However, if P is false, Q could be true, or Q could be false, and that covers all the possible combinations. Now with a disjunction, P has to be true, or Q has to be true, or in this case, both could be true. So in the first line, P is true and Q is true, therefore the disjunction is true. In the second line, because P is true, the disjunction is true. It doesn't matter that Q is false because it's an or. In the third line, because Q is true, the disjunction is true. But finally, because they are both false and neither one of them is true, now the disjunction is false. Again, looking at this in terms of sets, if we define P where X is a factor of 24, and Q where X is a factor of 18, drawing up our sets, looking at factors of 24, we've got 1 and 24, we've got 2 and 12, we've got 3 and 8, 4 and 6, 5 isn't a factor and 6 is a repeat, so they're all the factors of 24. All the factors of 18, 1 and 18, 2 and 9, 3 and 6. 4 isn't a factor, 5 isn't a factor. So looking at that in common, we have 1. 2 is also a factor of both. 3 is also a factor of both. 4 is only a factor of 24, so 4 goes in here. 5 isn't a factor of either, so that goes out of here. 6 is a factor of both. 7 isn't either. 8 is a factor of 24. 9 is a factor of 18. And 10 and 11 are factors of neither. 12 is a factor of 24. Then we got 13, 14, 15, 16, 17, 18 is a factor of 18, 19, 20, 21, 22, 23 all outside, and 24 in there. Now the area covered by P or Q or both is like the union in set terms. It could be anywhere within the circles. So that's P or Q or both. Finally, we're going to look at the exclusive disjunction. And the symbol for this is like the disjunction, but there's a line underneath the V. And that means it's P or Q have to be true, but not both. So an example of this is if P is the proposition that you drink, and Q is the proposition that you drive. You can drink or you can drive, but you can't do both. So this is an example of an exclusive proposition. So again, setting up our truth table, we've got P, we've got Q, and this time we've got P exclusive or Q. So again, P can be true and Q can be true, P can be true and Q can be false, or P can be false, Q can be true, or they're both false. Now this time, because we can't drink and drive when both P and Q are true, the exclusive disjunction is false, because you can't drink and drive. However, when P is true, you can drink, as long as you don't drive, so that's true. Or when Q is true, you can drive as long as you don't drink, but that's true. And if you don't drink or drive, then it's a bit of a waste of a sober driver, so that is false. Again, in set terms, if we set P up as x is a factor of 12, and Q, x is an odd number less than 10, then if we were to draw this up in set form, factors of 12, there's 1, which is also an odd number less than 10, so that goes in there. 1 and 12, 12 isn't odd, so that goes in there. 2, again not odd, and 6, again not odd. 3, which is odd, and 4, which isn't. 5 isn't a factor. 6 we've already covered, so there's all the factors of 12. So looking at all the other odd numbers less than 10, sorry, I correct that. 5 should be in there, so 1's already covered, 3's covered, 5 is an odd number less than 10, 7 is an odd number less than 10 that's not a factor of 12, and 9 is an odd number less than 10. So the area covered by the Exclusive disjunction is anything that's in P but not in Q, and similarly anything that's in Q but not in P. So it's just this area, not the overlap.